Pluto is a far-off and bewildering minor planet, once an individual member of our planetary family. However, recent disturbing declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding revelation. They proposed that this cold world is on a collision course with Neptune. But how could this occur, and what may be the consequences of such a critical event? Are we seeing a charming, grandiose, capricious occurrence? Or is there something else to this oncoming boundless impact? Join us as we research the possible results of a Pluto-Neptune impact. Pluto, a previous planet that was scaled back to a dwarf planet, is noteworthy because of its odd orbit, and it remains a subject of interest and study in the astronomical community, as shown by recent assumptions by leading experts. Pluto's orbit is perilously close to Neptune's, and Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which would pose a significant risk to Earth. How is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our nearby solar system. It requires a complex 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even finished one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by its extraordinary bent shape, deviating significantly from the almost round orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination of 17 degrees to the ecliptic plane. The course Pluto follows is significantly steeper compared to other planets. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For at least 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we'd expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto slammed into Neptune? The answer lies in the gravitational impacts of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to determine its unique orbit. Unlike other planets whose orbits lie close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and bent shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three bodies like Pluto, Neptune, and the Sun move and affect each other through their gravity. Pluto's orbit is, in fact, chaotic. Minor deviations in initial conditions can lead to significant differences over long periods. However, these surprising properties of Pluto's orbit have been found to maintain stability over particularly long timescales, keeping tumult in check. Recent simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Jupiter's immense gravity is strong enough to keep Pluto on a stable path for potentially billions of years. These factors are crucial in maintaining order and consistency in celestial mechanics. Without these factors, our solar system would be a place of far greater chaos and unpredictability. Pluto's orbit is a striking representation of celestial mechanics at play, showing both stability and turmoil within our local planetary system. The unique characteristics of its orbit, affected by the gravitational forces of nearby planets, particularly Neptune, highlight the complex and dynamic nature of space. Predicting significant events, especially when it involves chaotic orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While mathematical simulations offer a solid means for understanding and predicting the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. So why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in cosmology, have expressed concern about a possible impact between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a captivating and catastrophic event in our solar system. The impact would release an enormous amount of energy, likely destroying Pluto due to its smaller size and icy composition. Debris from the impact could scatter across the solar system, possibly presenting a risk to other planets and their moons. For Neptune, such an impact could alter its current atmosphere and potentially its orbit, depending on the specifics of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the conversation. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital mechanics of celestial bodies like Pluto can yield significant knowledge for future space missions. This information can help in navigating the solar system more effectively, predicting potential dangers, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. In terms of planetary science, celestial mechanics, and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that might even connect to string theory. String theory, a theoretical framework where the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The impact could create extreme conditions of energy and gravity, potentially leading to circumstances where predictions made by string theory could become observable. For instance, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's mysterious dance around the Sun continues to fascinate scientists and enthusiasts alike, offering a window into the intricacies of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and reshaped our understanding of planetary bodies, later discoveries about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two prominent voices in astronomy, have raised concerns about a possible collision between Pluto and Neptune, shedding light on the complex forces at play in our celestial neighborhood. Their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern the movements of celestial bodies. Pluto's orbit, characterized by its eccentricity and steep inclination, defies conventional assumptions and challenges our perspective on planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, crossing with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, especially Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over many years. Despite the tumultuous nature of its path, numerical simulations and theoretical models play an essential role in predicting the future behaviors of celestial bodies and understanding the complex interactions between planets. These simulations show that while Pluto's orbit is chaotic over millennia, it remains relatively stable within the broader context of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Michio Kaku, underscores the ongoing uncertainties and unpredictability in planetary dynamics. While such an event remains speculative and highly unlikely in the near term, the gravitational dance between Pluto and Neptune highlights the delicate balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, the study of Pluto offers practical insights for future space exploration missions. NASA's New Horizons spacecraft, launched in 2006, provided remarkable images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water ice and vast fields of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of New Horizons mission highlighted the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies, and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, helping us understand planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to classify celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific categorization systems and the evolving nature of astronomical knowledge. While Pluto meets several criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet underscores the diversity of celestial bodies beyond the traditional planets. Studying Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are crucial for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary migration and the development of the Kuiper Belt, a region beyond Neptune populated by small, icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system's development. Understanding the intricacies of celestial mechanics can also inform future space exploration missions, including the search for habitable worlds beyond our solar system. By studying the movements of distant celestial bodies, astronomers can identify potential targets for future exploration and assess the feasibility of traveling to other star systems. The potential impact of a Pluto-Neptune collision, while highly unlikely, serves as a reminder of the dynamic nature of the universe and the unpredictability of large-scale events. As we continue to explore the outer reaches of the solar system and beyond, the study of planetary orbits and celestial mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from the paths of other planets, offers valuable lessons about the complexities of planetary motion. The stability of its orbit over long timescales, despite its unpredictability, provides important insights into the balance of forces that govern the movements of celestial bodies. In a sense, the ongoing study of Pluto's orbit and its potential interactions with Neptune mirrors the broader challenges of understanding the universe at large. With each new discovery and each theoretical model, we continue to refine our knowledge of the cosmos, uncovering the mysteries of distant worlds. As we venture further into the mysteries of Pluto and its orbit, it's important to consider the broader implications of studying such a distant celestial body. Pluto's orbit offers more than just insights into its own peculiar path. It serves as a crucial case study for understanding the behavior of objects on the outskirts of our solar system. Its position and interactions with Neptune underscore the significance of gravitational dynamics, which extend beyond our immediate planetary neighbors. These studies contribute to a better understanding of the Kuiper Belt, a region filled with icy objects that may hold clues to the early solar system's formation. One fascinating aspect of Pluto's relationship with Neptune is the resonance between their orbits. Despite the crossing of their paths, gravitational forces have prevented a collision by locking them into a stable orbital resonance. This resonance ensures that the two planets never collide, even though their orbits intersect at certain points. This mechanism of orbital resonance is not unique to Pluto and Neptune, but it highlights the delicate balance of forces that govern planetary motion in the outer solar system. Such interactions serve as a reminder of the complex gravitational dances that occur between distant bodies, making the study of such phenomena essential for predicting future changes in our solar system. Moreover, the study of Pluto's orbit could also shed light on the behavior of similar dwarf planets and trans-Neptunian objects located even further out in the solar system. These distant bodies may hold important clues to understanding the processes that led to the formation of the solar system. By studying their orbits and the forces that shape them, astronomers can gather valuable data to inform models of planetary system evolution. The potential for future missions to the outer solar system is enhanced by our understanding of Pluto and its dynamics. The success of the New Horizons mission to Pluto opened up new avenues for exploring these far-off regions. As we plan missions to investigate other Kuiper Belt objects or distant exoplanets, the knowledge gained from Pluto's exploration will undoubtedly guide our strategies and technological innovations. Whether or not Pluto's interaction with Neptune leads to a collision, the ongoing study of Pluto remains vital for expanding our knowledge of the cosmos and the intricate workings of our solar system. Studying Pluto also provides essential insights into the formation and evolution of the outer solar system. The objects in the Kuiper Belt, where Pluto resides, are believed to be remnants from the early solar system, offering a snapshot of conditions that existed billions of years ago. Understanding how these bodies interact with each other and with the giant planets like Neptune can help scientists piece together the puzzle of planetary migration, where planets and other objects move over time due to gravitational interactions. These interactions are key to understanding not only our solar system's past, but also the dynamics of exoplanetary systems around other stars.